Light is truly amazing. It travels faster than anything else we know. It brings warmth from the sun. It lets us see the world around us. Now, scientists have done something incredible. They have made light behave in a new way. They have turned light into a special kind of solid. This is not just any ordinary solid. It is a very special state called a supersolid. Imagine light that has a fixed, ordered shape like a crystal, but at the same time it can flow without any effort like a perfect liquid. This combination is what makes a photonic supersolid so unique. It is a new form of matter made from light itself. This amazing discovery is very recent. It happened in our modern times, announced in 2025. It shows how much we are still learning. This breakthrough opens up a whole new field of study. Scientists all over the world are very excited. To understand how light can become a supersolid, we need to talk about quantum physics. Quantum physics is the science of very, very small things. It studies the building blocks of our universe. It looks at atoms and even smaller particles. It also studies light particles, which are called photons. This world of the very small works differently from our everyday world. The rules are quite surprising. In this quantum world, particles can behave in strange ways. For example, a tiny particle can be in many places at once. This is called superposition. Particles can also act like waves, spreading out instead of being in one spot. This is called wave-particle duality. These ideas are very different from how big objects behave. A football, for instance, is always in one place. Photons are the individual particles of light. Think of them as tiny packets of light energy. Usually, photons do not interact much with each other. If you shine two flashlight beams through each other, they just pass through. Making photons talk to each other and act together is a big challenge. This is exactly what scientists had to overcome to make a photonic supersolid. Quantum physics provides the rules that govern these tiny particles. So what exactly is a supersolid? The name itself sounds very special, like something from a comic book. It is a specific state of matter. We know about common states of matter. These are solids like ice, liquids like water, and gases like air. A supersolid is much rarer and much stranger than these. It was predicted by scientists many years ago, but it has been very hard to create and observe. A supersolid has two very distinct properties at the same time. First, its particles are arranged in a regular repeating pattern. This is like a normal solid. Think of the atoms in a crystal of salt or sugar. They form a neat, ordered structure. This structure gives the solid its shape and rigidity. The second special property is called superfluidity. This means that some particles can flow through this ordered structure. They can flow without any friction or resistance at all. It is like a liquid that, once set in motion, would never stop. This frictionless flow is a purely quantum mechanical effect. So a supersolid is a truly bizarre state of matter. It is both perfectly ordered like a crystal and allows for perfect frictionless flow like a superfluid. How did scientists manage to make light behave in this extraordinary way? The first big challenge was to trap the light. Light, as we know, loves to travel. It moves at an incredible speed, about 300,000 kilometers per second. It does not like to stay in one place. So to make it form a supersolid, scientists first had to catch it and hold it still. This required a very clever setup. They used special materials called semiconductors. Semiconductors are materials that can sometimes conduct electricity and sometimes not. They are the key components in modern electronics. You find them in your computer chips and smartphones. It turns out that semiconductors can also interact with light in interesting ways. The scientists designed and built extremely tiny traps for photons. These traps were made of thin layers of semiconductor materials. They were like microscopic cavities or boxes for light. The walls of these boxes acted like highly reflective mirrors. When photons of light were shone into these tiny cavities, they bounced back and forth between the mirrors. They became trapped inside this small space. Once the photons were caught inside these semiconductor traps, they could not easily escape. Section 5. Building with light. How the supersolid was made. Simply trapping the light particles or photons was not enough. For light to become a supersolid, the photons needed to interact strongly. They needed to coordinate their behavior. They had to arrange themselves into that special, ordered yet fluid state. This required even more quantum magic. The scientists had to carefully control the conditions inside the tiny traps. Inside the semiconductor traps, the photons started to mix with the material itself. The light particles interacted with something called excitons. Excitons are like tiny packets of energy within the semiconductor material. They're formed when light excites electrons in the material. This mixing of photons and excitons created new hybrid particles. These new mixed particles are called polaritons. Polaritons are fascinating because they are part light, photon, and part matter, exciton. Because they are partly matter, they can interact with each other much more strongly than pure photons can. By carefully adjusting the conditions, such as cooling the system to very low temperatures and shining specific lasers, the scientists guided the polaritons. They encouraged them to settle into a specific arrangement. The world's first photonic supersolid was created. Section 6. A bright future. Why this discovery is exciting. This discovery of a photonic supersolid is a very big deal. It shows that we can control light in ways we never thought possible before. This newfound control over light could lead to many new and exciting technologies in the future. Imagine creating new types of lasers that are incredibly efficient, or think about new kinds of sensors that can detect tiny changes with amazing precision. Perhaps the most exciting idea is light-based computing. Computers that use light instead of electricity could be much faster. They could also use less energy. Photonic supersolids might provide a new way to build components for such quantum computers. Photonic supersolids are also a fantastic new tool for studying quantum physics itself. They provide a unique system where scientists can observe strange quantum effects. They can test fundamental theories about how matter and light behave. This helps us deepen our understanding of the universe at its most basic level. The ability to make light behave as a supersolid is truly remarkable. Section 7. Tricky science challenges in making light solid. Creating a photonic supersolid was an extremely difficult task. Light, by its very nature, is elusive and energetic. It does not naturally want to be confined or forced into an ordered structure. Overcoming this fundamental characteristic of light was the first major hurdle. It required a lot of clever thinking and careful experimentation. The experiments also needed incredibly low temperatures. We are talking about temperatures close to absolute zero. Achieving and maintaining such extreme cold is a major technical challenge. It requires sophisticated cooling equipment and very well-insulated environments. Even small fluctuations in temperature could disrupt the delicate state of the photonic supersolid. Furthermore, the tiny traps used to catch the light had to be fabricated with extreme precision. These semiconductor cavities were often smaller than the width of a human hair. Any tiny imperfection in their structure could prevent the photons from being trapped effectively. This demanded advanced manufacturing techniques and meticulous attention to detail. Section 8. Lighting the way. What's next for photonic supersolids? The creation of the first photonic supersolid is a landmark achievement, but it is really just the beginning of a new scientific adventure. Scientists now have many more questions they want to answer. They are eager to study these novel states of light in much greater detail. They want to fully understand all their unusual properties and behaviors. One important goal for future research is to try and create photonic supersolids at higher temperatures. The current experiments require extremely cold conditions. If these states could be made closer to room temperature, it would make experiments much easier to conduct. It would also bring any potential technological applications much closer to becoming a reality. Researchers will also explore making different types of photonic supersolids. They might try using different kinds of semiconductor materials, or they could design new types of traps for the light. These explorations could reveal even more exotic behaviors of light. Perhaps there are other, even stranger quantum states waiting to be discovered. Section 9. Beyond imagination, new science, new tools. Transforming light into a supersolid is a truly astonishing scientific feat. It fundamentally changes our perception of what light is and what it can do. For centuries, we have thought of light primarily as waves that carry energy, or as streams of particles. Now we see that light can also organize itself into complex, structured states that have properties of both a solid and a perfect fluid. This discovery provides powerful new evidence for the strange and wonderful rules of quantum physics. It demonstrates that the bizarre effects predicted by quantum theory are not just abstract concepts. They can be harnessed and observed in laboratory settings. Creating a photonic supersolid shows our increasing ability to control the quantum world. This knowledge is incredibly valuable as we seek to understand the universe more deeply. The advanced tools and techniques developed to achieve this are also highly important. Building the tiny, precise semiconductor traps and controlling the interactions of polaritons required new experimental methods. These methods can now be adapted and used for other cutting-edge research. They help us to probe and manipulate matter and light at the nanoscale. This, in turn, will undoubtedly lead to even more discoveries in the future.